Okay, our second speaker is Andrei Okounkov, who I mentioned 1 hour ago is also a member of the HMI board. Andrei been here many times. He is our good friend, and he's from Columbia University, and also had won many prizes, including Fields Medal, more than 10 years ago, 20 years ago, maybe. No. Something. Sorry, I forgot. Andrei, as I said, is a frequent visitor, comes to help us run the Hamilton Mathematics Institute. We want to thank Andrei to accept our invitation to come again. His title today is Eisenstein Spectrum. Before he starts, I want to remind you that then there will be break and the public lecture will be at 7 o'clock, so please don't forget that. Thank you, Andrei, please.
Thank you. Thanks so much for this introduction and for the chance to speak in this magnificent setting. It's great to be here at the Trinity College where history is alive and feel the connection of time, and great to be part of the celebration. Congratulate Samson and his institute on the many successes, and of course I hope that when we celebrate 200 years of your institute and simultaneously the 400 years of Hamilton, this will be the connection of times will be just as uninterrupted as it is today. It's wonderful. So I'm going to talk about something I've been doing in recent years with David Kashdan, and so in this talk we'll see much simpler singularities than in Maxim's talk. We'll see just poles, and there will be three kinds of poles, or rather, a pole is a pole, but the poles will have three kind of separate origins. One of them would have to do with the resolvents and the spectra of the operators. That may be the part that's the most directly connected to Hamilton's legacy. Another would be the poles that appear in zeta function in Eisenstein series. And finally, we'll talk about the pole when you sum up the geometric series, you get a pole, and the geometric meaning of that pole that will occupy us in the third part of this lecture. And so we'll start with spectra. And so I will begin by this very, very basic example. Consider a finite difference operator which acts on functions on non-negative integers by taking a function to its more or less its average at x plus 1 and x minus 1, but there is asymmetry with the q. Q will be bigger than 1. In number theory, q has to be a prime power, but here just any number bigger than 1. And in other words, this is a Hamiltonian of a quantum particle that hops on the half line with slight asymmetry, and there's reflecting boundary conditions at 0. And it's elementary to see that this has a continuous and discrete spectrum. Namely, it has two eigenfunctions, namely function identical. Well, I didn't say, so this is operator self-adjoint with respect to a certain simple measure, and that measure is such that function identical equal to 1 is an L2, and so that's obviously an eigenfunction, and function that alternates goes 1 minus 1, 1, 1 minus 1, that's also will be an L2, eigenfunction with another eigenfunction. And aside from these two eigenfunctions, it has a continuous spectrum filling the segment from minus 2 root q to 2 root q. And so this means that if I look at the resolvent, so resolvent is you take your operator, you subtract the complex numbers, and you invert it. So by definition, that's a holomorphic operated valued function for all z's outside of, that's the definition of the spectrum, in fact. For all z outside the spectrum, that's a holomorphic function. And this will be at a point where you have an actual eigenvector, this function will have a pole, so the resolvent will have a pole at z plus minus 1 plus q. And a continuous spectrum is kind of like it's like in electrostatics. If we want a continuous distribution of charge, well, we take one charge, we integrate it. So if you integrate the pole, you get a log, and the log is a function that has a cut, so the resolvent will have a cut along the continuous spectrum. And in fact, there's some well-known formulas in quantum mechanics. In mathematics, they're called Stone formulas. I'm sure in physics there's some other name to that. That says, well, I don't know, maybe physicists also use the word Stone's formula that tell you what's the eigenvectors and what's the spectral projectors for a self-adjoint operator in terms of the singularity of its resolvent. And our goal today is to read off the same information from the behavior of so quantum mechanics is about some Hilbert space, L2, for instance. And so an eigenvector for us is a solution of a certain difference equation that's square integrable. But there's also solutions that are not square integrable. They're non-normalizable eigenfunctions, sometimes Yost functions, maybe other names. And it's, in this particular instance, very easy to write them down because after all, it's an operator with constant coefficients, so it will have you can write an eigenfunction elementary. And so you write an eigenfunction of the form. So it's convenient for many reasons. It's convenient to shift things by root q. And so let's see. The eigenfunction will behave somehow exponentially at exponentially for large x. And so let's write it that it behaves as root q times some parameter a raised to the power x for large x. And then, of course, this is, since our operator acts on this function, on this particular asymptotic operator acts in an obvious way, that the eigenvalue of this eigenfunction is the symmetric combination. Take root q times a plus 1 over a. And incidentally, this function, a plus 1 over a, is the one of the Zhukovsky airfoil fame. And when we teach complex analysis, one of the kind of beautiful facts we teach is that that function will take the outside of the unit circle, will go precisely to, so the unit circle will be collapsed under this map to exactly the segment, to exactly the unit circle will be collapsed 2-to-1 to exactly the continuous spectrum, and the outside of the unit circle will go to the complement of that, to the complement of the spectrum, and the points plus minus root q, they will go to the discrete spectrum. So now, so this is kind of the next point. We talked about these Yost functions, that non-normalizable eigenfunctions, and so they're not normalizable, but you can consider things called wave packets. That is to say, you take a linear combination of non-normalizable things, and you might as well find something which is normalizable. And in fact, in this particular situation, we have a function which is analytic for large A, and we can take its counter-integral against anything we want, for instance, Laurent polynomial. And so that's very easy to see. That would be not just in L2, in fact, we have compact support, so it's even better. So this will be dense in L2. And evidently, if we want to apply a resolvent of our operator to this wave packet, all we need to do is just act on the function under the integral sign, and so this will have an explicit result of the resolvent applied to such function, of course, explicit. And from this formula, so what are we supposed to see? We're supposed to see, so from this, what are we supposed to learn from the resolvent? From the resolvent, we're supposed to learn that where are the singularities? So the singularities of the resolvent correspond to spectrum. That is to say, a pole corresponds to the eigenfunction, and a cut corresponds to a continuous spectrum. And okay, we have this explicit integral. We look at it, and then we see how we can get a pole and how we can get a cut. And again, this is pretty obvious. What's going to happen is that this Yost function has to have a pole at exactly the points where this function lambda sends to the eigen. So at this two little dots that the function lambda sends to the discrete spectrum, the eigenfunction has to have a pole. And the cut will come from the simple fact that my map from the unit disk to the spectrum is 2 to 1. So if I come from to the unit, depending on to which of the 2 points in the unit circle I come, I get 2 different sides of the cut, and that's how I get a cut and the result. So while this, of course, is maybe my only goal in this transparency, in this set of slides, was to somehow activate the neural circuits in the brains of those who've seen this in their undergraduate years, or maybe teach it, or somehow relate this to maybe the core mission of Hamilton Mathematics Institute. I maybe will summarize what happened at this set of slides by this slide, is that you can, in fact, while this is how, I don't know, I mean, maybe not all people, at least some people, came to think about the subject, it may be easier to invert the logic and look at things from a slightly different angle. So we have an operator, this Hamiltonian. We have a set of functions which are eigenfunctions, but not square integrable. So they by themselves not in our Hilbert space. However, if we form a wave packet, that is to say, we integrate our non-normalizable function against, say, Laurent polynomial, then we go to L2, and that is to say, so if I take the space of Laurent polynomials, then I have a linear map, namely integration against the normal function that takes Laurent polynomials to my Hilbert space. Now, in my Hilbert space, I have an interesting operator, the Laplace Hamiltonian, I should say, in this conference. And by the very definition, this map intertwines this operator with just multiplication by a function lambda. Right, so this is, in my Laurent polynomials, my operator is already diagonal. So in that sense, so usually we think in when we do spectral theorem, we usually think that we have a Hilbert space, and that Hilbert space, the structure of the Hilbert space is something obvious. You take a norm of the norm of the element. If you take the norm square of your function, you integrate. That's like the Hilbert space structure. But the operator is complicated. Here, this elementary linear map already diagonalizes the operator. The operator already is multiplication by a function. But the norm is something that we need to be analyzed. And what we did before is we took the definition of the norm in some kind of integral, and when we say, let me examine it, what will happen with resolvent as I approach some point, what we effectively did is we took the contour of integration for this wave packet, and we shrank it as close as we could to the unit circle. And the result of that, we wrote our norm would be written as a sum of integral over the unit circle, which is the contribution of the continuous spectrum, and the 2 poles that we pick. So that the decomposition of the space into continuous discrete spectrum that came from the fact that I took my contour integral that defines my wave packet, and I tried to move it as close as I could to where I think is continuous spectrum. And then I picked some poles, and that's the result of it. That's my spectral theory. But in fact, you don't. All you need is the end result. Like if, so maybe I'll just somehow to make the logic as simple, as transparent as possible, all you need in this setup. So you have, when we talk about spectral, some kind of spectral analysis, all we need is, we already have a linear map that diagonalizes the operator. We have some way to describe what's the norm. And if we have some way to present the norm as a contribution from all suspected, if we can present the norm as a contribution from all suspected parts of the spectrum, then we're done. There's nothing else. In other words, how we here from the penultimate line to the left, from the penultimate to the last line, the passage we did was by some kind of contour deformation, but it doesn't have to be. If you have some way to take that norm and write as a contribution of various pieces, then you're done. I'm sure I'm either bored you to death or maybe, well, anyhow. So that's all I wanted to say in this part of the talk. Now, the next thing we'll talk about Eisenstein series. And I don't want to insult anybody's intelligence, but let's remind ourselves what is Riemann zeta function. It's given by either sum or product. And looking at the product, you might think the poles in this function come from the poles of the terms in the product, but in fact, the zeta function has a one and only pole at s equals 1 and analytic elsewhere. But the more symmetric version of the zeta function that has to do that you add a certain Archimedean factor to that. Then it satisfies, this is called psi function. Then it satisfies the functional equation on the nose, namely psi of 1 minus s equals psi of s. And then, of course, the price for that to pay is that if you have such functional equation and you have a pole at 1, then you must have a pole at 0. So that function has two poles at 0 and 1, and of course, zeta function has a many generalization mathematics, which we will meet too. Namely, we will see the zeta function and the psi function of some general global field. So here we were. Instead of the previous zeta function had to do with rational numbers, and you were summing over rational integers, and there were rational primes there. For general global field, there's the corresponding notions. And another generalization are the Eisenstein series. So what's the Eisenstein series? So the classical Eisenstein series is a function of a unimodal lattice. Unimodular means the area of fundamental parallelogram is 1. And what you do is you sum over, you take a vector, which you can assume, we will assume, or classically is assumed to be primitive. And then you sum over all these primitive vectors. Primitive means not a multiple of another vector. And you will sum, just like you were summing, so in the zeta function you sum n to the s. Here you sum the length of gamma to, well, not exactly to the s plus 1 is a better convention. And this, just like a zeta function that converges for sufficiently large s, has a nice analytic continuation, functional equation, and has a pole at s equals 1, just like what the zeta function used to have. And of course, if you do it for instead of a two-dimensional lattice, if you do it for one-dimensional lattice, then that doesn't have so many primitive vectors. But if you drop the primitive condition, then it'll be just like zeta function. Right? So you'll be summing. The possible length of your vectors will be multiples of the length of the generator, and you're doing Riemann zeta function. And in any dimension for lattice of any rank, you can drop the primitive condition at the expense of just a zeta function factor, because if you drop the primitive condition, you're just summing over multiples of a given vector, and that's a zeta function. So one way to think about primitive vectors in a lattice is, of course, if I have a lattice, a primitive vector is just, there's, well, up to plus minus, there's one for every slope, right? So if I just give myself some rational slope, which could be also infinite, then for every rational slope, there is a primitive vector, and it's minus, but we're dividing by 2, so somehow it doesn't really matter. So this is So this is we're really summing over rational points in projective lines. So if we take all rationals and add infinity, we're summing just the same of rational points in projective line. And this is something you can do this has something you can generalize, namely projective line over rationals. This is, first of all, it's a homogeneous variety, so it's SL2 modulo its Borel subgroup, which you can replace by any other homogeneous variety, such as flag manifold, whatever, something, Grassmannian, something. And then, of course, you can replace rationals by the same global. I told you the rational is an example of a global field. You can put any other global field there. And then you'll have and what we're summing, so we have a rational number. We represent it as n over m, and then we're computing the length of the vector n comma m. Right? So that's like a notion of a height of a rational number, and you similarly can do sum over points in a homogeneous variety or an arbitrary global field. You sum, you take a point, take its height, raise it to the power s, shift appropriately, and put denominator. That'll be the Eisenstein series. And they have very similar properties. They have functional equation. They have analytic continuation. And if you think so this is, I started with the classical Eisenstein series, which is a function of a lattice. Now, the space of lattices is, we all seen in one form or another. This is the upper half plane modulo SL2Z. This is beautiful geometric figure which is not compact, has a cusp corresponding to lattices that have a very, very long vector and a very, very short vector. And it has two singularities corresponding to lattices that have extra isometries, namely the square and the hexagonal, the triangular. And as on that space, there are canonical, on the space of lattices, there's somehow extremely canonical Laplace operator, and in general, it's generalization for other groups other than SL2. There'll be more canonical invariant differential operators, but there's also canonical difference operator called Hecke operators. And in fact, what happens is this Eisenstein series is an eigenfunction of all these operators, and it's never an L2. And in fact, we saw an example of that is because if it's a global field, we take rational. So what are the global fields? The global fields are either finite extensions of the rationals or finite extensions of rational function of one variable with coefficients in a finite field. So if I take rational functions, if I'm a global field, I take rational functions in one variable with coefficients in a finite field FQ, then the analog of the space of lattices is that half line we saw in the first example, and the Hamiltonian is the Hecke operator. And this function E, the non-normalized eigenfunction, that's the Eisenstein series. So this general situation, again, we have some Hilbert space, namely L2 on the space of lattices. We have canonical commuting self-adjoint operators. We have eigenfunctions, none of which is an L2. And what do we want to do? We want to find the actual spectrum. So the problem that goes back to Selberg, I think, but certainly very extensively studied by Langlands and many, many distinguished mathematicians, was to find the spectrum of Laplace and Hecke operators in the span of Eisenstein series. So in general, this L2 on the space of lattices that has, or L2 of these automorphic forms, that has a certain decomposition in which some part has to do with Eisenstein series and other stuff, cusp forms, etc. But so you want to find the space, the eigenfunction, the eigens, want to find the spectrum of Laplace and Hecke operators in the span of Eisenstein series. And how do you describe that span of Eisenstein series? Well, you might as well think about the wave packets, that's like as we did before. So what would you do what sort of wave packet you would consider? Well, the Eisenstein series is it's a function of S. It's analytical. It's convergent for S sufficiently large, like zeta function converges for S sufficiently large, and so then we can take this Eisenstein series and integrate it against any function we want. So let's integrate it against function f of s. Now, what does it mean? So the Eisenstein series was sum over all vectors, and we're applying linear operator to that sum. We might as well interchange the order of summation integration. So what we're effectively doing with summing, we're going over all primitive vectors in a lattice, and we applying some function to the length of that vector, where the function f check is this Mellin Fourier transform of the function f. So this Mellin Fourier transform being bidirectional in certain spaces, we might as well assume that f check is as nice a function as we would like. We can make this f check to be compactly supported, infinitely differentiable. That's enough. I think this is, so you can take the best bump function of the length of the vector you take, and this is and sum over all vectors in a lattice value of that function of the length of the vector. This will be in the span of Eisenstein series, and this will be certainly square integrable on your modular space of lattices, etc. And so that it's in the space of these things that we would like to compute the spectrum of Laplace and Hecke operators. And this is, like I said, this is a very, very old problem in mathematics. And there were like very, very old problems in a very, very important area. There are, of course, very challenging conjectures about them. And there are some generalities to those conjectures, which I'm not going to discuss maybe I'm not qualified to discuss them in complete generality. Well, just an application to Eisenstein series in this talk. And this conjecture relate the spectrum of this Eisenstein spectrum to something. So you start. I remind you, we talked about Eisenstein series for SL2, but SL2 could be replaced by any group over any global field. And you ask this question for this group G, and what you're supposed to discover, you're supposed to discover nilpotent elements in the Lie algebra of the Langland's dual complex group. And for SL2, what this means concretely, for SL2, this Eisenstein, well, I didn't discuss, for SL2, I already discussed the more complicated finite, the more complicated Q case, so then the less complicated case, it's easier to discuss. So for SL2Q, this means that the Eisenstein spectrum, there is a function identical equal to 1, and that's a 0 eigenvalue of the Laplace operator. And the rest is a continuous spectrum that starts in 1/4. And so these two pieces of the spectrum correspond to the two kinds of nilpotent elements in SL2, namely the actual 0 element, which corresponds to the continuous spectrum here, and the non-trivial nilpotent that corresponds to the discrete spectrum, consists of 1 point. And this is Q to 1 limit from the picture we discussed before, namely if instead of SL2 of Q, I take SL2 of function field in one variable, then the spectrum is the space we discussed, the shape we discussed, and the way the labeling goes is that the continuous part corresponds to the 0 nilpotent, and the discrete part corresponds to non-trivial nilpotent. And how do you identify these pieces in the spectrum is the following. So let this Zhikovsky function from part 1. So in part 1, we were taking A plus A inverse. And the Joukowsky function is just the trace of the matrix A and A inverse. So this you recognize A times NV inverse is the generic conjugacy class in SL2. And you take the trace, so that's your function. And the spectrum is described what sort of elements of A will I allow. And the elements A I allow are labeled by nilpotent element E. And the way this looks is like that. So for every nilpotent element, so this is just a general piece of Lie theory. For any nilpotent element in any Lie algebra, there is always another element called H, such that the commutator of H in E equals 2 times E. In other words, this is if you think of algebra SL2, the Lie algebra SL2, you write it usually in the basis F, H, E, and H is the middle element of that guy. And so now in these terms, I'm going to tell you what sort of A's, how do I label the values of A in terms of nilpotent elements. So this A inverse, which is, again, is you should think of some conjugacy class in SL2. That conjugacy class should lie, in the first approximation, it should lie in a compact subgroup. But more precisely, where it will lie, so the maximal compact subgroup of SL2 as SU2. So more precisely, it may lie where? So if I have a nilpotent element, I can look at the centralizer of that nilpotent element in the compact subgroup, and then I can allow certain non-compactness by multiplying by Q to the H over 2. So let's see how this works in this example. So I have, for SL2, I have 2 nilpotent elements, 0 and the non-trivial one. For the 0 element, this SU2, the centralizer of E in SU2, that's the whole SU2, says A inverse is in SU2, that is to say absolute value of A equals 1. That's the continuous spectrum we saw. And then there's a non-trivial guy, which says that the commutator, so if I have a non-trivial nilpotent element, that the only thing in the compact subgroup that commutes with it are just plus minus 1, plus minus that density matrix. And so then I'm saying I'm getting Q to, I'm saying that A equals root Q times plus minus 1. So A equals plus minus root Q, that's the position of discrete spectrum we saw. I imagine most of you were following this computation, but even if you did, it's something you can reconstruct very easily at your leisure later. And so these conjectures, like I said, there's all conjectures, and they've been approached through kind of the old methods of quantum mechanics, namely you take a counter, you deform it, and Langlands himself, I'm not sure Langlands was actually aware of this existence of these methods in quantum mechanics, or he just rediscovered them. That I don't know. I'm a little afraid to talk to Langlands, but I'd be curious to know what the story was. So he did, in his book on Eisenstein series, he devotes something like 15 pages of that book doing the counter integral for the group of G2, and that's if you want to learn how to organize counter integration in a way great minds organize counter integration, you should read that. You should read that book. The whole of that, I imagine, but that's kind of a great example of how you organize things. And he found one interesting point, which corresponds to the fact that for one unexpected point in the spectrum, it corresponds to the fact. So this is a very, very long computation, and then pretty much everything cancels out. But there's remaining one interesting contribution, and that corresponds to the fact that in Lie algebra G2, there is one interesting nilpotent element, so-called subregular nilpotent, which is. And so concretely, what sort of computation was Langlands doing? You can write this. So we have. So we were in the situation when we already diagonalized our operator, but we don't know how to write the Hermitian form in a nice way. And the first thing he does, Langlands writes, and this is called Langlands constant term identity, that the Hermitian form can be written as a form where you integrate over lambda, where lambda is now generally a vector. Vector has as many components as the rank of the group. And you integrate over lambda, and then there's a part which looks like a standard thing you'd write in any Hilbert space. And then there's something which looks like, if you're doing many body particle kind of things, this would be you would call these things reflection coefficients. And these reflection coefficients, they come with the ratios of this zeta function for your global field F. So by the functional equation, instead of shift by +1, you can, so by the functional equation, this alpha, this psi of something +1 is the same as psi of minus that thing, so that will be even more, maybe more familiar to you. And so this is, and what you need to do is you want to take this contour to, so this is a contour, you should imagine this is a contour in Lie algebra, you want to take it to the Lie algebra of the compact group, that is to say, to purely imaginary. So this contour, you want to move to purely imaginary, picking some residues along the way. And that's, like I said, if you want to gauge the complexity of this procedure, read Langland's computation, which is two-dimensional integral. So for the group of E8, and there is now computer-assisted computation for E8. So this can be done, but for the group E8, you're facing, although it's 8-dimensional integration, but maybe it's okay. But there are two things the two big numbers you're facing, and one big number is the order of the Weil group, E8. So when on my computer I type this number, the computer thinks it's a phone number and suggests to add a contact. But more importantly, there's just in terms of what sort of, if you think where at what sort of places you have to look for singularities of that integral, and the singularity of the integrals are the singularity of zeta functions, so they're along the reflection hyperplanes. And this sort of thing intersect in all possible ways. So if you study all possible intersection of all these hyperplanes, you're basically looking at 10 to the 12 various residues to analyze. So it's a big task to compute it. But by contrast, as complicated a group E8 is, it only contains 70. 70 is a big number for Lie theorists, but it's much smaller than the other numbers on this slide. It only has 70 nilpotent conjugacy classes, and those can be easily. My students in Lie theory class can describe those elements. So I remind you how we're supposed to invert the logic, the inversion of the logic that we already, in some sense, we already diagonalized our operator. All we need to do is we need to have some way to write the norm. Right? So we need to. So in other words, when we form this wave packets, our operator. So we have a map from functions of lambda to our L2, and this map already. All the Laplace and Hickey operators, they're already diagonalized by this map. All you need to do is you need to understand what is the norm. And if you know what you expect, what the answer, you know what they expect, what sort of answer you're supposed to expect, then okay, what are we supposed to do? I told you in general terms what the spectrum of all these operators is supposed to be. So the norm, the L2 norm of the function f with our new space, well, that should be what? There'll be component for every nilpotent conjugacy class. It's a sum over E, and then for every nilpotent conjugacy class, well, I told you what the spectrum is supposed to be. It has to do with some conjugacy class. So here in the Lie algebra situation, it's what do? You take the Lie algebra of the compact form, that is to say more imaginary direction in the subspace. You take whatever commutes with E, so it will be linear subspace, and you shift it by half of this element H called characteristic. So you shift it by half of the characteristic. That's where the spectrum is supposed to be. So this L2 norm of this wave packet has to be sum over nilpotent elements, and for each nilpotent element you integrate over something, and then there should be spectral measure, spectral projector. No? So if we have that, then the spectral theorem is established. Right? So that makes sense. All right, so this brings us to this to part 3. Get myself some more water. So we looked at this at the geometric series, and one way to look at it is to say that's a trace. It's a trace of what? So you take this 1 plus a squared and so forth is a trace of an element with eigenvalues 1, a squared, and so forth. And where do we find this element? Well, if we look at polynomials in one variable x, and our transformation a scales that x by a, then we'll scale x squared by a squared, x cubed by a cubed, and so forth. And so when we take the trace, we'll find the geometric series. In other words, this geometric series is the trace of an element A that acts on functions of one variable, that is to say functions on a line. And what it does, it scales the coordinate function by A. Well, it scales all other functions by however it's supposed to scale them. In this language, incidentally, the polar locus is kind of easy to describe also. That's just the set of all these elements such that their fixed locus is not compact. But that's a side remark. That so far so good? So moreover, if you ask what's the multiplicity, so if I have, so A is an element in A is some non-zero scalar, so I can think as an element in unitary group or an element in GL1, and that group has representation, namely where A goes to A to the K. And if I ask what's the multiplicity of that representation, well, what am I supposed to say? I'm supposed to, one way to say it, I can write like analog of orthogonality of characters, namely I want to take the complex conjugate or the dual characters, let's say A minus K, and integrate it against my trace. And I have to integrate, of course, I have to integrate it where my trace is convergent. So I have to integrate it where the absolute value of A is less than 1. Right, so this counter-integral, this particular counter-integral, we should think of this. So how do we use characters in representation theory? If I have a trace of some, if you have a character of some representation, we can use we can find the multiplicity of any reducible by integrating it against the character and using the orthogonality of characters. In that sense, if I want to, for my particular representation, namely my group U1 or JL1 acting on functions on one variable, this trace 1 over 1 minus 8 together with the counter of integration is in that sense, for every representation, it outputs its multiplicity. So it's either a holomorphic distribution GL1 or ordinary distribution on U1. So in the language of it makes, so this character is not just a rational function, but together with a choice of counter of integration, that is a distribution. A distribution really takes any character and tells you what's the multiplicity of that character in my representation. That makes sense? So this can be generalize as follows. So for some algebraic variety x, well, if it has to have any function, better be non-compact. So then we look at so we have some non-compact algebraic variety x. We look at functions on that algebraic variety. And if we have an automorphism of variety, such as scaling of my line, this will act on functions, and very often this action will have the property that any given irreducible representation occurs with finite multiplicity. So I have a well-defined distribution, namely assigns to a character of distribution the multiplicity with which it appears, and that's, like I said, you can view it as either real distribution in the compact form or holomorphic distribution in the compactification. And once we've done this, of course, you can generalize it in two ways simultaneously. One is, when I look at functions, we're not multiplying here anything, we're just adding things. So instead of functions, we can look at any module over functions, that is to say, so anything which is a finitely presented module over functions called coherent sheaf. So for instance, sections of a vector bundle. So it doesn't, the elements of with functions, we don't have to multiply, we just add them. So instead of functions, we can take any module over functions. And say, well, the ones that are globally defined, these algebraic geometries called the zeroth cohomology of the corresponding coherent shape, but you might as well look at higher cohomology. It's very, very, very natural. And so out of this, you can form a particularly important combination. So if I have one of these coherent sheaves just finally generated module over functions, and I can look at all of its cohomology, and I form alternating sum. That's called the Euler characteristic. And that's why it's so important. It's so this Euler characteristic, assuming that my group acts. So all of these spaces are infinite dimensional in principle, and my group acts in these spaces somehow, but I assume that the action is such that the multiplicity of every irreducible is finite, and so all these corresponding traces well defined as distributions. And the Euler characteristic have two basic properties: that if it's additive in both the sheaf and the space. So this late in the talk, I think maybe those of you for whom it's obvious, it will probably remain obvious even if I try to explain it more. And if you've never seen it before, maybe you can just believe me that this is the Euler characteristic. There is a way to add spaces and the way to add sheaves. And so the function is additive in both. And that is to say that the computation of this distribution factors, instead of taking some unspecified sheaf on some unspecified algebraic variety, that really factors through something relatively understandable. And so we now remind you what was from part 2. We were looking for, so maybe I'll just go back to that point here. Right, so here, right? So we were looking. We have this diagram. So we have functions of parameter lambda that we use to make the wave packet, and then. So this diagonalizes my Hecke Laplace operators, but what I want a quadratic form on that space of functions. And since the multiplication by anything invariant is given by my operator, this form, if I multiply on either side by invariant function, this multiplication I can move from one side of the scalar product to another side of the scalar product. In other words, when I look for norms, when I talk about norms, where do I get it? Here. So when I talk about norms, I'm looking not necessarily for a linear functional functions, tensor functions, but tensor functions over W invariant functions. Because if I have a W invariant function, this multiplication by that function, I can move from one side of the inner product to another side of the inner product. And mathematicians now, since I talked about K-theory and stuff, mathematicians now, of course, should recognize that if I have functions, tensor functions over W invariant functions, that has to do with cohomology or K-theory or something of the flag manifold. And in fact, the manifold that the particular space we want to look at, we take, so flag manifold, so it has to be for the Langlands dual group, and the flag manifold for the Langlands dual group is G check mod the corresponding B check. This looks slightly asymmetric. Better to check. One can take the quotient by B on the other side. That's not going to change. That's not going to change the cohomology. And for us, it's also important to take the T star of that, but not of that. Either the quotient by B check on the other side or T star doesn't really affect the homology. So the space we're looking for a linear form on something which is essentially homology of flag variety. And in fact, this linear form has what's it going to be? We're looking for this inner product in the space of this wave packets. So it has to be, strictly speaking, it has to be linear in one argument and antilinear in the other. And what it's supposed to be is that it's the Euler characteristic on that flag, on that relative of a flag manifold of the class which is you have a class on one side, you have a class on the other side, you pull them back to the product, and then you take the outer tensor product, and then tensor something, whatever, doesn't really matter. And so maybe I'll skip the transparency. So at the beginning, I gave the reference for the slides. So you go to my webpage, and it's called Eisenstein _talk.pdf. So maybe you can, if you're curious about this kind of what are those dots? Maybe you can just at your leisure look at that, and maybe we'll. But the most important thing about this, so what we're gonna what's the end game? So the one thing about why did we want the cotangent of the flag manifold? Because the cotangent of the flag manifold, so if you have a Lie algebra, then the set of nilpotent elements in this Lie algebra is some interesting singular algebraic variety. So for instance, if you take a 3x3 matrices, let's say real, 3x3 real matrices with trace 0, then the set of nilpotent ones are the ones which where determinant vanishes, and that would be a cone. So that would be like an ordinary cone. In general, it has a more complicated singularity, and the singularity has a resolution called the Grothendieck-Springer resolution, namely the cotangent bundle to the Langlands dual flag manifold maps its resolution of singularities of the set of all nilpotent elements in the corresponding Langlands dual Lie algebra. And so this is, if instead I go from T star of this double quotient, then just descending from the previous construction, I will have a natural map to the set of nilpotent element up to conjugation. I have one more transparency, so we're good. I'm good. Yeah. So this is we're good. We're gonna make time. No worry about that. So let's just this is a beautiful classical piece of mathematics. For those of you who don't know, maybe I'll say it one more time. There's the reason we're looking to find something has to do with nilpotent elements in some Lie algebra. The first thing we do is we look at the set of all of them. It's some cone. And that is resolved by the cotangent bundle to the Langlands dual flag manifold. So there is a map from this cotangent bundle to the nilpotent cone. Now, this map induces a map from the cotangent bundle to this double quotient to the set of nilpotent elements up to conjugation. That set has finitely many elements. So there's the finitely many, so it's some kind of stack, but the number of points are finite. There are finitely many things. There are finitely many nilpotent for any Lie algebra, the set of nilpotent elements has finitely many conjugacy classes. And there's some understanding of the orbits of that map too. And so, what are we going to do? We wrote our bilinear form, or Hermitian form. We had an Hermitian form, and we wrote it as an Euler characteristic of something on the space X. Euler characteristics corresponds to taking homology, that is to say, push, kind of derived push forward to a point. You take any space, maps to a point, you take homology is you pushing forward something to a point. Instead, you can, if your space maps to something else, and especially if that something else has finitely many orbits, then this Euler characteristic will decompose into sum of finitely many elements. So the fact that we wrote an Euler characteristic on a space that maps to something with finitely many points, that already is some decomposition. Already we wanted to find a sum, this the sum. Now we wanted to find a sum of integrals. Where is the integral supposed to come from? So each nilpotent conjugacy class is not really, we're looking at nilpotent element up to conjugation. But given nilpotent element, we'll have elements that commute with that. So this is, when you want to take the Euler characteristic on point mod centralizer of nilpotent element, means you have to find, means you have to compute invariance of that group acting in whatever you had before. That is to say, by Weil integration formula, this will be integration over compact form of that centralizer. So the fact that we find sum of integrals is because we had finitely many points, each is something point modular group, so you get the integration just from what's the Euler characteristic on point modular group. And if you look more closely, we were supposed to find what sum of integrals and then spectral projector and the spectral measure, and spectral projector and the spectral measure you also find from this diagram. So it's maybe, and now I'll stop. Yeah.
Maybe it's just intuitive what I feel here. There are many things that you said, I believe I understand, many I don't understand. Mm-hmm. But I would say this Eisenstein spectrum either is a version of Hitchin spectrum or the other way around. Because many things you talked about show up when we studied Hitchin integrable systems, which are related to, as you know very well, to quantum homology of some models in supersymmetric theories and so on. So is there any relation? Or I'm just feel like that Hitchin and Eisenstein...
Maybe you should ask Nigel.
No, Nigel. I'm asking you. You're giving a lecture. Okay, let me...
So maybe I'll...
Sorry. Let me make more.
Yeah.
So, for example, slug manifold replaced by Grassmannian, cotangent bundle to slug manifold replaced by cotangent bundle of Grassmannian. Now we're in business, because now this is what's called XXX spin chain, which we know how to use to calculate quantum homology of the T-star to Grassmannian, as you know. So somehow, one step farther would be Hitchin.
Okay, maybe I can tell you a story.
Okay,
I don't know if this will be. So this is just how did it happen that David and I started working on this?
Okay.
So this will be, will take me 3 minutes to say that. So in this beta gauge correspondence that you know so well, there is very good understanding of the eigenvalues, right? Spectrum. But it takes a while to develop the understanding of eigenvectors.
Well, you did that some time ago.
Right. And in fact, you can find not just the eigenvectors, you can find, so eigenvectors is it's like a stationary problem, but you can solve the Knižnik-Zamolodchikov equation.
You mean the quantum version?
Knižnik-Zamolodchikov. And in a way which is more efficient than what people more general and also more efficient than what people did before, because in the situation when the QKZ was solved before, of course people, what was people write, you take basically integrate off-shell. One sec. You integrate some kind of off-shell beta function, off-shell beta eigenfunction, but then when you try to prove its satisfy equation, you have to move the contour of integration, and this geometric ways which originate from the stuff you mentioned, give you a way to solve the QKZ without doing any of the contour of integration. Without moving any contour of integration. And so I was lecturing about this in Kazhdan seminar, and Kazhdan said, well, if you can do it without moving contour of integration there, you should be able to do it without moving contour of integrations here. And for a few months, I thought that this will have to be some kind of quantum geometry again. This here is a question about some kind of point count equals just the Euler characteristic on something like a Fallach manifold itself. No spaces of maps, no nothing. But for the first, originally I was thinking that you have to do some kind of spaces of maps. But in fact, for the spectrum, you don't. For the spectrum, it's only the classical part that contributes to the spectrum. If you want finer properties of Eisenstein series, then indeed you will find some integrals over spaces of maps, etc. But the spectrum only determined by just the classical term.
There was a reason why some people, like me, would be less interested in finding a vector, because we are taught in quantum mechanics that wave function depends on which coordinates you write. So it's basically, but spectrum is universal. You can actually measure the energies. That's why we were focused on the spectrum. This is first. And the second, for Langland's dual group in a Hitchin system, right, there is a way to think about quantum Knižnik-Zamolodchikov as a second quantization of that one. So if Hitchin quantizes first integrable system, then you take a Langland's dual, go to the other side in geometric Langland's correspondence, and now you have another integrable system which you can quantize there, and it introduces a second thing. And that's a QKZ, and you do write the wave functions there as coming from the gauge theory, as you know very well.
Right, but
so we avoid those kind of problems from the beginning if we want to study the spectrum. We don't need that. But anyway, just comment. I apologize. I apologize.
With all due respect, I think eigenfunctions are good too. So
what? What was that?
Well, I think spectrum is great, but knowing something about eigenfunction is, cannot hurt.
Yeah. So the spectrum they measure, when they run the accelerators.
Yeah.
I'm sorry, I asked many questions. Maybe we take a couple of more and then we wrap up. Yeah. Well, I have to apologize again because this talk was so interesting for me that I had to jump in. Sorry, Andrei. Okay, let's thank Andrei again.